Why was the casket empty?
Why would it say that?
All right, y'all. Welcome to atomic structure. Sounds easy, yeah? Hey, what are the three subatomic particles in the atom that would make up its structure?
Proton, electron, neutron.
Yes. Y'all finally knew something. I'm just kidding.
I was reading a book.
Hey, so there's three particles that really make up the general atomic structure. However, two of them are not really going to be discussed. We're not really going to talk about protons and neutrons very much. We'll do protons a little bit, but that's actually a different field of chemistry. Anybody know what field of chemistry really studies the protons and the neutrons?
Microbiome.
Might know.
It's
Where are they located?
Nuclear chemistry.
Nuclear chem. Oh, look at that. Figured out he was right after he said it. I like that. Did y'all see what I did? Hi. Okay. What? Oh, I don't know his name.
No.
All right, so what we're going to be focusing on then is that third particle, mostly, which is, of course, the electrons. But electrons have always been the most interesting. Oh, well, I didn't follow it up. Nuclear chemistry is not covered in the AP curriculum. So we won't be doing cool fission and fusion, and we won't be doing decay reactions and the cool radiation stuff. So, sorry. It's outside of our scope. But anyways, we are going to be looking at electrons in several different ways, and we're going to start off by looking at it in a way that we did last year. Most of today was from last year, but these pre-AP topics are on the exam. So electrons have the ability to produce light. Now, light in and of itself is described as having duality, which we're not going to really talk about in here because it's also outside the scope. But does anybody know what it means that light is described as having duality?
It can act both as a wave and as a particle.
It's described as acting both as a wave and as a particle, and it's super interesting to study, just not with me. So, with all the many ways, did you bring your phone out?
Well, I copied tomorrow's lecture instead of today's lecture.
With all the many ways that we can look at electrons, we're going to start with their ability to produce light. So, we need to revisit our friend Max Planck. What Planck was able to derive is a standard number that represents the amount of energy given off basically in like a flash of light. All right? Now, if you look at Planck's constant, you'll notice it's a very small number, which makes sense because you don't want all of this light surrounding you to be giving off huge amounts of energy all the time, or it would affect you daily. So, it's a very, very small value. What you might remember that we did last year, though, is using Planck's constant, we were able to calculate connections between energy, frequency, and wavelength of light. And of course, it's the electrons that produce the light, which makes this a valid thing to study. Your AP sheet is going to give you two equations covering Planck's constant. It's going to give you the C equals lambda V, and then it's going to give you the E equals HV over there. Now, sometimes those are enough, but if a problem leaves out frequency as one of the variables, then I taught you last year, if you were one of my students, that you have to use both equations. You use one to get a variable you need for the other. You can still do that. However, since you're timed on the AP exam, I think it benefits you better to memorize this bottom equation. That equation that I'm currently pointing to is not on the AP sheet. All right, for those of y'all at home, I'm pointing to E equals HC over wavelength. All right? It is not on the AP sheet, but using it makes you move faster and has less room for error. So, let's take a look at a couple Planck problems that you could run into. All right, so the first one says calculate the energy of photons of orange light, and it gives you a frequency. Now, when frequency is a part of the problem, that means that the given equations are both totally usable. All right, like this one, for example, is going to use E equals HV. All right, which is given to you, as I said, E standing for energy, H the variable for Planck's constant, and V the variable for frequency. All right, so while this will become a simple plug and chug, I do want to point out that your units are absolutely vital, because due to the units of the constant values, the other items require proper units be put into the equation. So I put them at the bottom just so you know. So if you're given a unit that doesn't match what's provided there, you need to do a simple conversion. But in this case, we're all right because your seconds there are good. So to solve for energy then, I'll take H, which is Planck's constant, of 6.63 E negative 34. And we want to multiply that by the frequency, which is a given value in the problem. See if you can quickly get an answer.
Is it pronounced Rylan or Rylan?
It's Rylan. Are you reading the book or are you doing chemistry right now?
I'm doing multiple things at the same time. But
I don't know if that works for you.
is it Rylan? It's Rylan, but it's spelled like Dylan, but with an R. It would be Rylan.
He said, oh, really?
Did y'all get that as your energy?
Yes.
Now, the next problem doesn't use frequency, which, again, if you don't have the extra equation in your back pocket, it becomes a longer problem if you're using just what's given on the AP sheet. So if we use the one that I think you should just know, which is E equals HC over wavelength, you'll have an easier time. But there's an additional problem. What's the issue in this problem?
You don't have.
You don't have the way.
No. We have everything we need.
We do.
All right. Well, meters is length, right? That's fine. These are both constant values.
It's in yeah, that's
It's in nanometers. All right. We're not missing anything. It's just the number that they gave us is in units that we're not allowed to use. So let's start off then by doing a unit conversion. So let's go, what is it, 428? 425. So let's take 425. Let's use pretty dimensional analysis so that the FRQ people love us. And I want to change it to meters because that's the acceptable unit for wavelength. All right, so we'll put nanometers down here and meters up top. And now you have to know a conversion factor. You are supposed to know the prefix nano. What was it?
9.
It was 9. Very good. 1 meter is the same as 1 E 9 nanometers.
Sorry. Gabe remembers your characters from the book.
Who?
Gabe?
Are you Rylan?
What?
Are you?
I wouldn't make myself the main character.
You said light blue eyes.
You totally would.
Quit looking at my eyes. And I get 4.25 E negative 7 meters, which again, all we've done here is a conversion. Now we can plug and chug. All right, so we're looking for energy. So we'll go E equals HC. H is Planck. All right, and we're supposed to be multiplying that times the speed of light, another constant value that you're given. That's 3e8. And that's supposed to go over the wavelength of 4.25 e negative 7.
I want to know.
No.
I want to know.
It's nothing bad.
Put it away. This is
AP Chem, you don't have time to do that.
Scare me. Stay away from me.
I get 4.68 e negative 19.
Sir, what is the number?
Do you agree?
Maybe.
All right, let's move on then. So another handy thing that you're definitely going to want to know, all right? There have been several FRQs I've come across that it benefits you to know the order by which these waves get stronger. So I want you to memorize next to these waves of radio waves through gamma rays. It's easy. But there's several times in the past where being able to do a comparison of them really shows that you know your stuff and encourages you to get the point on a question.
Like when we had that one question in the game, and it's like, which one? I knew it. I was sitting in the back mad because somebody only put one way to find.
Will they give you the...
I would have had those extra points. I would have gotten an 8.
No. So the question was, will they give you the chart thing? You need to know your visible spectrum, Roy G. Biv, all right? And I'm saying that you also want to know the related order of waves. None of that will be given to you at all. All right? So make sure you're just able to compare them in general. What's stronger than what? Remember, red is weaker than violet, so that will be your best connection. The other conclusion that we drew from this last year was the connection between energy, wavelength, and frequency, and we looked at a drawn wave. It was the same day that we went to the dark room. Do y'all remember doing the light lab last year?
I do.
No.
You remember going to the dark room and I broke the oh, you suck. Now, but one of the conclusions we drew that day is the wavelength gets larger, further distance. Well, that means the waves are happening less frequently. So the frequency goes down as the wavelength goes up. And if anything is happening less frequently, well, then there's less energy. If you're not mowing the lawn frequently, then you're not spending a lot of energy mowing the lawn. So those two things are directly connected, frequency and energy. But both of those compared to wavelength have an inverse connection because they go opposite waves. Ways, no pun intended. I had a Dylan moment. I didn't realize I was funny until after I said it. As wavelength gets larger, the energy and the frequency gets smaller, and vice versa. All right, well, a little bit more review. If you remember the birth of photons, when a mommy and daddy love each other very much.
How many times has he said that in his class?
What?
How many times have you said that in his class? Because I've heard that.
It's in the Cat in the Hat. Yes, I have daughters. I want you to know where photons originate, which are going to be the packets of light. So as a reminder, electrons have a ground state. That is the orbital by which they're expected to be found. If those electrons absorb energy from a source, they become excited. And when they become excited, they will then jump further away from the nucleus into a different orbital. Now, depending on the amount of energy absorbed will dictate the distance that they get to jump. But then on the trip back, they have to get rid of that energy. They can only return to the ground state if they're no longer excited. So, on the trip back to the ground state, they will shed the energy, and depending on the distance they travel, will dictate the color of the light. Because if it's a further distance, that means they absorb more energy, and of course, higher energies are connected to different colors of light. So, that is our general process of creating photons. Electrons get excited, return to the ground state. It's on the trip back that light photons are given off. So how do we know this? Well, let's take it a tiny step further. The experiments that were run to figure out the science behind this is called spectral analysis. I actually have a machine back there that's covered in so much dust that, not back there, back there. That's covered in so much dust that I can't read the manufacturer, but I'm gonna plug it in this weekend and I'm gonna see if we can come up with something cool to do next week with it. But here's what happens. Using the machine, you can get these emission readings, all right? And this is bad because it's not in color. But if you have the slides pulled up, you can see that the top has the entire visible spectrum available, all of the colors of the rainbow. And that's where an electron would start, with the availability to absorb any of those energies. When it does absorb the energy, it actually takes them with it. And you can see on your slide, if you're looking, that on the top, there's slivers of color missing. Well, that's the moment that an electron has become excited and it's taken that energy with it. Then, when it returns to the ground state and we use the machine to get another reading, you can see the light that's given off. And lo and behold, it's the exact same ones that it absorbed. So there's a direct connection there between the amount of energy it absorbed, the amount of energy it gives off, which will be equal, all right, and the color associated with both of them. So we can use the machine to do this spectral analysis and show this for different elements. And what's really cool is that the spectral analyses of elements is like a fingerprint. They all have their own. So you can take an unknown sample and put it in the machine, read the spectral analysis, and figure out what it is that you have, as long as you've got the data of the way that different elements react when their electrons become excited.
We've done this, but in Euclid.
Yes?
Don't they do this to know how big space is or something like that? And they send it out, and then they get the things going farther and farther away, so space is growing or something.
Yes.
Wait, what if the electron just stays excited and never goes back to the ground state?
There has to be a Disney World for that to happen. That was funny. I had never told that joke before. Look at all the other videos. I've never told that terrible joke before. It won't.
He's gonna watch back the videos and be like, that was a good one.
It won't. It will. It'll always go back to its ground state. All right. So I have a gift for you. I feel like I don't hand y'all very much stuff, but I know that y'all might be rusty on this review. So. It's the flu. I coughed on all of these individually. It took me all out.
Who are you? Oh, I still have to.
Oh my god, it's lunchtime.
Oh.
I remember not knowing.
I don't want to go back. You're going. No, it depends on whether or not I get back here. I don't. Yes.
Like transport?
Okay, would you get back here?
Diego, don't blow my mind, please. Okay.
I mean, that's what I heard. Okay, I read, sorry.
He went science. All right, so let's remember some of the information on this sheet. First off, you will definitely not have this in front of you for any test in here or on the AP. All right, this is just a crutch to help you get back in the mode of configurations. If you remember, there are 7 energy levels. They count straight down the table, 1 through 7. There's 4 letters that count as sublevels, S, P, D, F. and they get more complex in that order. And then there were different notations that are commonly used to describe the way electrons are configured in an element. And it tells you, they can tell you their shape and their energy and how many there are, how close to each other they are. And it lists the 3 notations you learned last year that you'll certainly still have to know this year.
Bought the book. I've been reading off a sample, but now I have the book.
Oh, you bought it?
Yeah. Expect 99
I get to eat
cents.
lunch today. Okay. The first one's 99 cents. They get more expensive. Because once I hook you, I'm like $80 for book 2.
Really?
Just kidding. No.
I'll pay.
It's $1.99 for book 2.
$1.99.
What do you think I made
Does
this
it go up
money?
like to $2.99?
The last one's $3.49.
Oh my god, you didn't even make it $3.50, $49.
That's a way above my budget.
We're gonna watch the video where teachers study.
Yes, that's what people do. I thought it was cool.
You weren't.
You make me poor.
Anyway,
Now I got a while.
so you'll need to be able to answer some specific questions about the energy levels and sublevels, and we're going to practice doing that. This slide is kind of unnecessary. Starting in 2014, AP quit testing the orientations of P's, D's, and F's. So I threw it in there just because I don't necessarily, I think it should still be tested. But anyway, the reason that the P, D's, and F have these different orbitals existing is because they're oriented in different ways. But I don't want to waste your time on something you're not going to be tested on. So let's move on to what you will be tested on. So while we're talking about electrons and orbitals, I want to remind you the general way that we would draw it. If you remember, we would show an energy level with a number, and then we would show a sublevel with a letter. And then what did we use to show an orbital if we were going to show it? Yeah, a line above. All right? And then there's the general rules. How many electrons can fit in one orbital?
2.
And what was true about those 2 electrons?
They were
They spin different directions. Now, does anybody remember the scientist that said that they behave like that?
Oh my god.
Albert
Wait.
Einstein.
No.
Doesn't it start with a P?
It starts with a P.
No.
What? Did you say cap?
Wait,
Polly.
Wait, what's
Anyway.
that biology kept?
Polly, it's fun.
No, not at all. So this was our general setup, all right? But one of the things that you were asked commonly to do, or that you will be asked to do, is to count the numbers of orbitals or sublevels or electrons at different levels of the table. And you can just do it. Like, for example, if I were to say, how many orbitals are there in energy level 2? How many orbitals are there in energy level 2? You can look at that chart and count it.
6.
All right? 6 is wrong.
7.
Oh, wait.
All right? Well, there's 2 S. How many
Three,
orbitals?
three.
How many orbitals does an S hold?
2.
1. All right? But then there's another sublevel at energy level 2. What is it?
Oh, it's 8.
2p. All right? How many orbitals does a p hold? 3.
Oh.
All right? Is there a 2d?
No.
No. So let me go back to the question. My question was, how many total orbitals are there at energy level 2?
I'm going to say 4.
There's 4. Now, you can figure it out that way. Or you can figure it out this way. If we would have used this new little cheat, we could have done it without having to think so hard. Because if the energy is 2, and I'm looking for the number of orbitals, what is 2 squared? 4. All right? So it'll make your life a little bit easier if you want to use this shortcut. Which part? The entire, from the beginning?
No, just like the
All right?
letter.
If I name energy level 2, all right, the entire energy level, not a specific part of it, energy level 2, and I want to know how many electrons there are, all right, I would say, well, 2 squared is 4, and 4 doubled is 8. So there's 8, all right? And look, and watch. 2, 4, 6, 8, if I wanted to fill it up.
Did you write these out last year?
You're going to still have to write them out, sweetie. But
You might have not read it.
Did you?
36. But there's not 36 orbitals.
All right, so let's talk about that. Man, I feel like I paid you to say that. Now, remember what we are... What we are doing is quantum theory. Theoretically, the periodic table could just be a piece of what exists, which means the reason it's really good to know these shortcuts is because only one time that I can find did AP ask a question like this. But I don't remember what the number was, but they asked something along the lines of, how many electrons would there be in energy level 27? Okay, well, like Dylan just said, there is no energy level 27. That's a stupid question. This is a theory. It's all a theory. But you could figure it out. Doing it like this, that would be annoying. But doing it like this, you could figure out the electrons. It'd be 27 squared times 2. And it would give you the theoretical number. All right? So you could use this shortcut to analyze items that are not actually on the table if you were asked to do so. For the next slide, can you cover it so it's a question at a time, even though they have access on their phone? Or on their, you know what I mean. All right, so we want to not get tricked by practice because the wording here, even though some of you feel good about this, I guarantee that Aspen is about to make somebody feel less good about themselves, all right? Because you're going to miss this because you're not reading carefully enough. So, Carolyn, Yohi. Okay, so let's go question for question and see if y'all can do this. All right? So I know y'all can already see the questions where you are. We're going to draw cards and get some volunteers. But the first question says, how many sublevels are there in the second energy level? Let's go to cluster 3, seat 3. 3. How many sublevels are there in the second energy level? His answer is 4. Do you agree or disagree?
Disagree.
Now, the reason that you can't use the shortcut here is because it's not pinpointing any of your shortcuts. All right, your shortcuts are giving you orbitals and electrons. So really what it's saying is at the second energy level, all right, how many different sublevels are there? Well, sublevels are letters. All right, we kind of already answered this question once, actually. Sublevels are letters. How many different letters are there?
2.
S.
There's 2. There's a 2S and there's a 2P. All right? So the answer to number 1 is 2. Next question, please. The next one says, how many orbitals are there in the third energy level? Now our shortcut can be a little bit more powerful. Cluster 4, seat 2. 4-2, what did you get?
9.
Her guess is 9. Do you agree or disagree?
Agree.
I agree. All right? She used the shortcut by going 3 squared. 3 squared is 9. And you can go count it individually, but why? All right, next question, please. How many electrons are there in the fourth energy level? Let's go to cluster 5, seat 6, Aspen.
64.
Her guess is 64. Do you agree or disagree? All right. So the shortcut she tried to use was... Y'all think everything is really funny today, and I don't think so. All right. Is 2x squared, right? Or 2n squared it uses on your paper. All right. And we assign the number 4. So if n is going to be 4, what's the first thing the order of operations says to do?
Sorry, you told me the answer.
I
4 squared, exponents first. Please excuse my dear Aunt Sally.
I never learned that. What?
Anyways.
4 squared is 16 times 2 is 32.
Careless.
Ding, 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 ding.
Yes.
I think it was a 10.
I think that was attendance.
Next question, please.
Wait.
How many electrons fit in the 2s sublevel?
Go back. With vengeance.
Excuse the interruption.
Yes,
Can you please send Giovanni Bez to attendance to his point home?
on his way.
Thank you.
Let's go to cluster 2,
No.
seat 5.
What does that mean?
It is all semester long. How many electrons can fit in 2s, do you think? In the 2s sublevel. All right, so let's think through it here. Think through it with me. 2s. All right, how many orbitals are in that s? 1. All right, so how many electrons can fit there? 2. There it is. Careful with the wording. Next question. How many electrons fit in a 2p orbital? Let's head over. Oh, I need to shuffle, so we'll roll. Let's go to cluster 5, seat 1. Aspen.
Now you want to do it.
How many electrons fit in a 2p orbital? Her guess is 6. Do you agree or disagree? The wording messes you up, right? Because I disagree with her. Let's take a look. It names 2p.
Oh wait, it's 2. It's just 2.
We know that 2p's got 3 orbitals. Now, what does it ask? In one 2p orbital.
Why'd you put it like that?
The answer, because they do. The answer is 2. 2. All right, show us our last activity of the day, please. So here's what's going to happen, y'all. We are going to, you have to be able to do the configurations. So I'm going to do the orbital notation with you, and then you're going to do the next 2 by yourself. I'm going to have 2 people come up and do it on the board. So let's do the longhand one together, though. So it wants us to look at manganese.
Magnesium.
No. Now, if you haven't noticed, on the wordy part of the handout I gave you, it explains how to do all this, all right? So you've got a crutch, as I said. Now, I know that manganese has 25 electrons by looking at the periodic table. Therefore, that helps dictate what my configuration should look like. Othball is the scientist that says we always start in 1s.
I'm scared.
Guys, it'll only hurt for a second. Polly.
It's a big one. Think they got skills?
Is it wait?
What's the country for Orbital? Is it Iran?
Are you getting this video?
Yeah, no, it'll be on video. And Polly says that we've got differently spinning electrons in an orbital. Now, remember, we have to account for every square on the table in order, and we read the table the way we read a book. So after 1s always comes 2s, and we know what a full 2s looks like. After 2s comes 2p. All right, and if you check your notes, p's got 3 orbitals. And then there's a third rule here, Hund's rule. What does Hund say?
It could go up and down.
Yeah.
They enter singly before doubly. So we're going to go up, 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 down, down, down. After 2p, if you read, comes 3s, followed by 3p. Now, you're supposed to keep count of the arrows, but you could have cheated by figuring out manganese's ending configuration before you started. But right now I'm at 2, 4, 6, 8, 10, 12, 14, 16, 18, so we're definitely not to the 25 that we need. After 3p comes 4s. And what comes after 4s?
3D.
3d, right? A little drop in energy. How many orbitals does a d have?
5.
Yes?
5.
I know. 5. All right, now remember, you show all of them, all right, no matter what, because like when we do hybridization, empty d orbitals are a big deal when we get to that next unit. But how are we going to fill this this level? Up, 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 up. Done.
7 down.
We have drawn 25 total arrows, and now I challenge you to do the other 2 notations for manganese. Again, the back of your sheet will help, but remember, these get easier. This is the long one, and we'll have somebody come up and solve for us, but you have to...
This is orbital.
That was orbital notation.
Orbital. I remember when we were testing on it in 3AP, and I didn't have this thing. I was like, I don't know what to do.
Michelle.
Shut up.
I'm worn out.
Are we done?
People are about to go right on the whiteboard.
Chemistry.
Oh, are we doing it before we come back? I'm so good. It's not gonna be me. What? Mr. Cummings, I don't know how to do this.
I know, like, I'm
Is
confused.
this told Rillin I love him, bro? Oh. I think it'd be interesting.
It'd be like the ones you filled in, so 1S2, 2S2. She's teaching me.
Oh.
Because I don't remember this.
But are you reading it off the sheet?
Yeah, and then the children like that was trying to. 2 pieces. 4S2.
Wait, hold on. I'm surprised it's the next one.
Hold on. Hold on.
Nick died.
1 second.
His brother died.
Stop spoiling it! He's only on chapter 2.
No, it's in the summary.
Like that.
This is what Nick got.
Wait, I need a.
Yeah, they're on the chair effect.
So you get to be friends with the kid named
Are we still just doing from
Cupid Road?
Is this on?
Yeah.
Is this recording still?
Look at that.
Is it recording still?
The one on the board is 4S3D.
So do I, so I go 3D
We're just shoot it down. I ran.
We'll walk up to it and go. Okay. In my pants.
Wait, why do we need periodic tables?
So where are you going now?
From the noble gas.
Get this?
Closest to.
Wait, what?
Wait, none of you have periodic tables?
I don't know why do we need a periodic table?
No. God dang it. Is this still recording?
Yeah, it's recording. If I flipped off the camera, would you do that?
Wait, what's this book called?
I wouldn't be surprised, but yeah, I'd do that.
Saga of Soul what?
Oh, I'll take that.
That's not how you say it.
Sorted?
That's not how you say it.
How do you spell it?
Sword dick.
I'm recording.
How do you say? Wait, no. How do you say it? How do you say it?
Like sword
Sardine.
dick. Sword dick.
We're talking about his book.
Saga Sardine.
No, I can't. It's Robin's.
Yeah, it's mine. It's Gabby's.
Oh, yeah, it's Gabby.
Oh, it's Gabby's. All right, so let's get somebody to come show us their handwriting.
Aspen is on you.
Let's go over to cluster 1, seat 4. Robin, come on up. Robin, come on up.
I refuse to be on camera.
Okay.
No!
Come on
I
up.
don't remember how to do it.
We'll walk through it together.
He said, okay.
She's doing a bad job. Just kidding. All right, so start with 1S. All right, but instead of, okay, so just write 1S. And then instead of drawing all the extra stuff, we're going to use an exponent. So put a 2 to represent the number of arrows you would have drawn. Now keep going. Oh. Do y'all consent?
How many FRQs are on the AP?
There's 3 long, 3 short.
Because, like, if they ask,
Why did I even sign up?
because if it's multiple choice, wouldn't you only be able to show that are FRQs? Or do you need to do
No, they have ways. All right, is everybody okay with that answer? All right, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, and the exponents added up equal 25. Let's have someone come show us their noble gas. Cluster 5, seat 1. Aspen, come on up.
It's Gabby.
He was like,
Oh, it is Gabby. Gabby, do you consent to being on camera? Okay.
It's Gabby's sister.
I have a question. Why did the test grade go up?
Did it?
She said 5 minutes last night in my sleep.
Is it your birthday?
Yesterday was.
Oh my god.
Okay, my handwriting's usually not that bad. Sorry about that.
Excuse me.
I don't know why I got so aggressive.
How do you say HARLQ?
It's a Hulk.
No. That element.
It's a Hulk. That's how you say it. They're godly beings. They're supposed to be hard to
How do
say.
you pronounce the book?
She said that.
Sordine.
Yeah, that's what I
Sortie.
Yeah, that's right.
Sordine.
Yeah, so she used argon as her noble gas because that was the noble gas that came most recently in the configuration, and then 4s2, 3d5.
3D.
Tomorrow is Beers Law. Have a good day.
I'll win the egg. I'll win the egg.